All right, so first we'll talk about limits because continuity is defined using a limit, right? So a limit is, or the idea of a limit is one of the ways that calculus is different from the algebra type courses, right? Because when we start talking about limits, we're really talking about where a function is approaching. We're talking about the tendencies. And then we really get into looking at, like the infinite number of points between even like one unit. All right. Okay. So in this chapter, we're going to define and calculate limits of function values. And then, like I said, we're going to use them to define and test for continuity. Okay, let's start with rate of change. Okay, so a moving body's average speed, right? Average speed, we know this, is found by dividing the total amount of distance covered divided by the total length of time. So if you got in your car and you drove 300 miles in 60 minutes, right? You can figure out roughly what your average speed was, right? Okay. The unit of measure is length per unit time for average speed. And the way we define it, the way we define average speed is f of t2 minus f of t1. Okay, what are these things? F in this case is the position function, right? So first we have to determine how much you traveled. Well, if you traveled, like 300 miles, well, how do you know? You started from here, you ended here. How much of a difference is that? So the way we do it is f of t1, if f is the position function, f of t1 is your starting position, and then f of t2 is your final position. So where you started minus where you ended minus where you started, that's how much you've traveled. And t2 over t1, again, t2 is the end time, and this is the beginning time. So we say the average speed is that over the time interval t1 to t2. And I believe there should be brackets around this, right? Do yours have brackets? Yeah. Okay. Sometimes when you convert to PDF, they go away. All right. So, take a look at this one. An object is dropped from rest. What does that mean, from rest? It wasn't moving. From the top of a tall building, and it falls y equals 16t squared feet. All right? That's the unit during the first t seconds. Find the average speed during the first 2 seconds of the fall. So what is it that we're given? This, okay, it falls that many feet. That is a position function, right? So this is your position function. And we want to find the average speed during the first 2 seconds of the fall. So the first 2 seconds means t goes from 0 to 2. So now I want f of 2 minus f of 0 over 2 minus 0. Okay, so that's going to be f of 2 is 16 times 2 squared. So I take the 2 and I put it into t right there, minus 16 times 0 squared all over 2. So this is 64 over 2, 32. Now, this numerator, right, it was the y, the f minus the f, and that position function is given to me in feet, so that is expressed in feet. The denominator is my time difference, and time is given in seconds, so that's seconds. That means my unit here are feet per second. Okay? All right. Here we go. Find the speed of the object at t equals 2 seconds and confirm your answer algebraically, right? So, all right, so let's do this. How are we going to do this? So I have the steps here. What we're going to do is we're going to calculate the average speed over the interval from t equals 2 to any time 2 plus h. Okay? So if we want the speed at t equals 2, all right, what I want to do is I want to find the average from 2 seconds to a little bit after that. So think about this for a minute. Whatever the speed was at 2 seconds, do you think it would be the same at 2 seconds and a nanosecond? Yeah. I think so, right? It would be pretty similar. Like it would be a pretty close approximation, right? So what I want to do now is this. I want to find the average, let's say, between what the speed was at 2 and a nanosecond after that, right? So why don't we go ahead and do that? Why don't we find delta y over delta t? This is the change in the position over the change in the time. In the time, 2 seconds to like just after 2 seconds. Okay, that very small amount of time. So let's do that. This is going to be f of the final position, so f of 2 plus h minus f of 2 over the final time minus the initial time. Right? So what we're looking for here is we're looking for the average velocity in the time interval, 2 seconds and like 2 seconds and a nanosecond after that. Okay? All right. So what's f of 2 plus h? We're going to take 2 plus h and we're going to plug it into our original function, 16t squared. So that's going to be 16, 2 plus h squared minus 16 times 2 squared over, how much is that? H. Is that familiar? Yeah? Okay. So here, this is 16 times 4 plus 4h plus h squared minus 64 over h. And this is 64 plus 64h plus 16h squared minus 64 over h. 64s will go away. So I have 64h plus 16h squared over h. What can I do now? Cancel out one h from everywhere. So I've got 64 plus 16h. Right? Okay. Now, what does this tell me? This just told me that the average velocity in the time interval, 2 seconds and like a nanosecond after that, is 64 plus 16h feet per second. Okay, so that's the first part. But that's not what I want. What I really wanted was the speed of the object at t equals 2, right? So the average between those two times is 64 plus 16h. But, so take a look here. We can't calculate the speed at the exact instant t equals 2, right? Because that means taking h equals 0, right? Remember, h is like how much time has passed after 2 seconds. If h was 0, then over here we would be dividing by h, and that didn't work. So what we could do, we can't say h is 0, but what we could say is, what would happen as h got smaller and smaller and smaller so that eventually it got close to 0? Okay? So here, what would happen as h eventually got smaller and smaller and smaller? So take a look here. I have, remember what I have here? 64 plus 16h. All right. If h was 1, and I plugged it in here, 64 plus 16, I would get 80. And then if I made h smaller, 0.1, the whole average velocity becomes 65.6. And then if I made h super small, what would the average velocity come close approach? 64. So then if I said, if I was looking for, so take a look here, this is time, this is 0, 1, 2, 3. If I was looking for the average speed between 2 and like the point right next to it, how much is h in this case? H is the difference between the red and the blue dots. How much is it over here? Pretty darn small. If h was that small, then that average velocity would be the same as the velocity at that point t equals 2. Okay? So as h approaches 0, the average velocity, the average speed, is a pretty close approximation to the speed at t equals 2. All right? So we talked about two different things here. One, we talked about average speed, total distance over total time. And then we talked about the speed at one specific point. And the way in which we went from that average to one specific point is, what did we do? What did we do to h? How much did we made it extra small. In calculus, we call it infinitesimally small. Infinitesimally small. All right, so like super small. You know, like infinity is huge. An infinitesimal amount is like, yeah, it's that small. It's like super small. All right, definition of a limit. Okay, so here is where we come into all these like crazy symbols. All right, so if f is defined at a point C, and left and right of C, and suppose f has a limit L as x approaches C, okay? Then, okay, so here's where it gets like mathy. There is a positive, okay. There is a positive number delta. That's the lowercase Greek delta, right? So that's the fourth letter of the Greek alphabet, lowercase delta, such that for all x, okay, what is the saying? It's saying as, whoops. All right, so suppose here at C, the value of this function is L, right? This is saying that if x minus c is less than delta, that means if you move a very small space delta to the left and right of c, the value is going to be pretty darn close to L. How close to L? Epsilon small close to L. Okay? Yeah. So that's the fourth letter, and that's the fifth letter of the Greek alphabet. All right? Epsilon. And, okay. So the way we write a limit is this. We know this, right? You've seen this before. And this says the limit of f of x as x approaches c equals L. That's how we read it. Okay? All right. I'm going to give you this sine of x over x. We're going to do it on our calculator. Let's graph this. This function sine of x over x is a famous function. It's like a celebrity among functions in math here. It's like if you met, I don't know, it's like if the functions went to a party, right? And they met somebody, I don't know, who's somebody famous that you'd like to meet? Nobody, huh? That many people. My. All right. Okay, so make sure your calculator is in radian, and we do zoom 7 for trig. What this does is it calibrates the x-axis so that the intervals are increments of pi and not just numbers. So, do we see this? Okay, so now take a look here. The function is the limit as x approaches 0 of sine of x over x. Now, take a look at sine of x over x. What are we dividing by? X. And if x was 0, not cool, right? Everything just falls, everything just explodes if we're dividing by 0. But what we're saying here is, what is happening as x is approaching 0? So x is like 0.000001 or negative 0.00001. Well, when we graph, we see that as x approaches 1, how much is the value of this function? How much? 1, right? So look, if I trace, look at this. At x equals 0, there is no y value because at x equals 0, is this function defined? No. It's undefined. But if I put in x equals 0.1, look at that. It's right next to it, and it's very much defined. If x is equal to 0.000 whatever 1, let's see if it's going to take it, right? Y is equal to 1. Even there it works. Do you see that? So as x approaches 0, the limit here is 1. Now, check out what we're going to do. This, you're going to memorize it. You're going to memorize it. You're going to memorize that the limit of sine of x over x as x approaches 0 is 1, because this comes up in a variety of different problems. This is going to be one of those problems where if I see you somewhere on campus, tap you on the shoulder and ask you, you should just tell me, yeah, it's 1. All right? We're cool? Okay. All right. So what we just saw in this function was at x equals 0. Yes, we were still able to find the limit, even though the function is undefined. All right? So, okay, so take a look at these 3 examples here. Look at this. At x equals 1, right? What's f of 1? What's f of 1 for that function? F of 1. Who said? Undefined. F of 1, it's undefined. There is no graph at 1. At x equals 1, there is a hole. There is nothing there. F of 1 is undefined. Now let's take a look at the limit. The limit is this. As I'm approaching 1 from the left-hand side, vertically, what value is the graph approaching? 2. As I'm approaching 1 from the right-hand side, vertically, what value is the graph approaching? 2. So here's the limit. If from the left and the right, they're approaching the same value, then the limit of f of x as x approaches 1 is defined. It's 2. Okay? All right. So let's take a look at the other one. Now this is g of x. What's g of 1? G of 1, I have a 1. Any other answers? I have a 2. I have an undefined. Any other answers? Okay. At 1, I look vertically, there is a dot at y equals 1. Yeah, there is a hole at y equals 2, fine. But that dot supersedes everything. So g of 1 is 1. Could we have figured that out using the equation? Look at the equation for g of x. It's a piecewise defined function. At x equals 1, it's that bottom equation that takes over, and the value is 1. Okay, what's the limit? Limit of g of x as x approaches 1. Okay, so I have, so let's see, I have a 2, I have a d and e. Let's see. As I'm approaching 1 from the left-hand side, what value is this approaching? 2. As I'm approaching 1 from the right-hand side, what value is this approaching? 2. It's approaching the same value. The limit is 2. So 2 cases so far. In one case, the value is undefined. There's a limit. Here, the value and the limit are both defined, but they're different. Okay, take a look at this one. What's h of 1? 2. Even with the equation, I plug in a 1, it's 2. Okay, as I'm approaching 1 from the left-hand side, vertically, where am I approaching? 2. As I'm approaching 1 from the right-hand side, vertically, where are we approaching? 2. So the limit of h of x as x approaches 1 is 2. So that's the third case where the actual value is the same. Moral of the story, when I'm looking for limits, I couldn't care less what the actual value of the function is. I don't care what f of 1 is. I don't care. I don't care what h of 2 is. I don't care. All I care about is where is the function approaching vertically. Okay? Yeah.
What does that say under the limit h of x equals 1?
It says x equals 1. Okay. Properties of limits. All right, so let's do some properties. The first situation, take a look at this. We have the limit as x approaches c of k. K is a constant. An equivalent example would be if I had, for example, the limit as x approaches, 5 of 3. What's my function? Y equals what? 3. In this case, my function is y equals 3. And let's see what that looks like. Oh, that's what it looks like. Y equals 3. Now, this is telling you, as x approaches 5, what is the limit? Okay, so as I'm approaching 5 from the left-hand side, what value is the graph approaching? 3. And from the right-hand side, 3, right? The function is y equals 3. That's a constant. Another way of looking at it is the function value is constantly 3. So the limit would just be 3. So here is that one, right? So look at that example. The limit as x approaches 2 of 3 would be what? 3. Okay. All right, so next, this is my limit. What's the function? What's the function? Y equals what? Y equals x. So let's graph y equals x. All right, what does that look like? Well, it looks like this. As I'm approaching, so take a look at this example. As x is approaching 3, what value is the graph approaching? 3, from the left and the right, right? So that's 3. So these are the two basic ones, and everything else is based on this. If the function is a constant, then that value is always the limit. If the function is the identity function, y equals x, then whatever the x value is, that's the limit. Everything else just transfers. Now look, I'm not going to go and recite these things to you. Basically what I'm going to do is, if you want the limit of f of x plus g of x, right? You do them separately. You find the limit of this, you find the limit of that, and you add them. All right? I'm just gonna go through examples because I know you've done this before. All right, take a look at this one. The limit as x approaches 2 of pi. What's the function? Y equals what? Y equals pi. Okay, so it's a horizontal line at pi. No matter what x value I'm at, my value is pi. Okay, here. The limit as x approaches a of this. So basically, just like we did here, where I could just plug in 3 for x, I could plug in a for each of these x's here. And so the limit would be 2a squared minus 5a plus 3. Okay. Questions? I think I'm gonna